Well, if the thinking parts of what we are pleased to call the 21st century agree on little else, there is a widespread conviction that the last word on the composition of reality and the principles that give it its character is finally to be drawn from the vocabulary and methods of science. This is not a conviction based on blind faith, but on the real accomplishments that have been made in physics and chemistry, medicine and biology, engineering, computer science, etc. The modern world is radically and qualitatively different from any preceding age, and the differences are largely the bequest of science. Science has earned respect and our confidence. Now, that much said, science is one of those troublesome nouns that seems to convey too little by standing for too much. Nobel Prizes are awarded in physics and in economics, but it is scarcely clear what those two subjects have in common, except that in some sense both are sciences, so-called. Then, too, there is political science, not to mention social science, not to mention what in the 19th century was called moral science. Many psychologists refer to themselves as behavioral scientists, or more recently, cognitive scientists. I needn't press on with Christian Science or Scientology to indicate the very broad reach of this noun and the seemingly arbitrary applications that are made of it. Well, it is the task of philosophy of science to consider a matter of this sort, to analyze the various senses of the term, to find such shared features as might justify the inclusion of otherwise disparate activities under the same general heading. There is, one might guess, little by way of doctrinal agreement between, say, Hinduism and Presbyterianism, but both qualify as religions. There is little by way of shared data between botany and astrophysics, but we say that both qualify as science. And so we ask, on what understanding does this come about? Well, it has been cogently advocated, especially by Carl Hempel during the 1950s and 60s, that the defining features of science are actually in the logical form of scientific explanation, and the restrictions on the class of events to be explained. These are the two features that determine whether something is a science. What kind of events are to be explained? What's the nature of the explanation? That is, differences in subject matter as such, in equipment, methods of inquiry, do not determine the status of a discipline as science. Instead, that status is earned by the special logic of scientific explanation and by the class of occurrences for which there should be such explanations. In his classic essay of 1965, Aspects of Scientific Explanation, Hempel defined an explanation this way, quote, he said it's an argument to the effect that the phenomenon to be explained was to be expected in virtue of certain explanatory facts, close quote. The mode of explanation then proposed has this general form. First, to qualify as an event that even warrants scientific explanation, the event in question must be empirical in principle. Now, this is not to say that science is indifferent to the other side of the moon, which can't be seen, let's say, at least long invisible. Rather, it is to say that the domain of what can be explained scientifically is the domain that includes what is, at least in principle, subject to observation. A shorthand way of putting the matter is to say that the sciences are empirical disciplines. Now let's take the textbook example of an object released from a height and falling. This is the sort of event that would qualify for scientific explanation. It's an empirical event. We refer to the statement of that which is to be explained as the explanandum statement, and that which provides the explanation as the explanans. Now, in this example, a falling object is the explanandum statement. Now, one way of explaining this is to say that experience teaches us that objects released from a height have always fallen, And so this instance is a warranted generalization based on past experience. This, however, is not what would characterize a scientific explanation in Hempel's sense. Rather, we would be inclined to turn to Newton for the right sort of explanation, to wit, all objects attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the squared distance between them. Now, as both the Earth and the item we've released are objects, they attract each other. Here, the object must fall just in case Newton's universal law of gravitation is true. Now, in this we have the essential ingredients of Hempel's theory of explanation in science. First, an empirical event to be explained, an object falling from a height. Second, there is a universal law specified which covers all events of this kind. In this case, it's the gravitation law. Third, though I didn't mention it, all the conditions relevant to the particular event have been specified or otherwise controlled. For example, the observations are made on Earth rather than on the Moon. The space within which the object is released is not made turbulent or unstable by other forces, etc. So there are these initial conditions we must specify. Now, with all this in place, we can say that that all such events are explained scientifically when they are logically deducible from a universal law known to be true. So the descent of the object is now understood not merely as something that reliably takes place, but as something that necessarily takes place just in case the universal law covering it is valid. Now, the Greek for law is nomos, and the anglicized adjectival form for lawfulness is nomological. Thus, Hempel's theory is called the deductive nomological model of explanation. He contrasts it with explanations based on inferences from past occurrences, referring to these as a mode of explanation called inductive statistical. So you're contrasting the inductive nomological with the deductive nomological. Now, considering this as the very criterion by which to qualify an enterprise as a science, well, the question naturally arises as to the status of those disciplines that lack universal laws, or are therefore unable to explain events by deducing them from such laws. Well, mind you, there are very few, if any, universal laws beyond classical mechanics. In fact, even Newton's laws have undergone challenge as a result of relativity theory. So what then can be said for much of biology and psychology in the matter of their scientific status, given that neither of those disciplines can explain events by deducing them from universal laws known to be true? Why is that? Because psychology and biology don't have universal laws known to be true. Now, this is where the inductive statistical model comes in. Hempel acknowledges that the most stringent criterion for a full-fledged scientific explanation will be missing from any number of disciplines otherwise understood on common sense grounds to be scientific disciplines. Well, what gives them this status, even though they're not in possession of universal laws? What gives them that status is their possession of statistically reliable relationships that do permit accurate and reliable prediction. Thus, the very statistical laws are, after all, reliable, and that must indicate that they are grounded in yet-to-be-discovered more fundamental laws. If there weren't more fundamental laws, all you'd have would be accidents and chance things. Now, there's no reason in principle, anytime you find regularities, to discount the possibility of some ultimate discovery of truly universal laws that then would permit a full-fledged scientific explanation. And as such regularities are already cataloged in biology, psychology, economics, sociology, well, these disciplines should qualify for full scientific membership, joining physics and chemistry, where work is also and always in progress. They're less developed, these other disciplines, than physics, but moving along the same path. Now, for all its neatness and intuitive appeal, the Hempelian scheme is, alas, plagued with problems. To some extent, the very statistical nature of reality itself, at least at the quantum level, raises questions as to the adequacy of a model of scientific explanation that calls for absolute universal laws allowing perfect prediction, etc. Then, too, the logical structure of Hempelian explanation leaves room for what turn out to be actually nonsensical examples, which nonetheless would qualify as scientific explanations. Consider this one, which was first suggested by Wesley Salmon. The explanandum: John is not pregnant. The initial condition: John is male. 2. John takes birth control pills. The explanans: no man taking birth control pills becomes pregnant. Now, we see that the event to be explained is indeed subsumed under a universal law bounded by these relevant initial conditions. There's nothing in the Hempelian scheme itself that would require us to conclude that John failed to become pregnant because men never become pregnant. Rather, it's the very neutrality of the model that leaves room for the possibility that it's because he took birth control pills, do you see? A further difficulty with the model is that it seems to permit spurious causal inferences. Consider an example that finds the indicator approaching empty on the fuel tank, and a universal law that declares when indicators are on empty, the car stops. Well, the event to be explained is the car stopping. The law in question seems to make this outcome the effect of a meter reading, as if it was the meter that caused the loss of motion. And again, the Hempelian model in its formal features doesn't rule out things like that. Now, the attempt to extend this model of explanation to the realm of social phenomena, those attempts produce yet another wave of compelling criticisms. Consider historical phenomena. Hempel is perfectly prepared to apply the model to historical phenomena, but one of Hempel's early critics, the philosopher William Drey, wrote a very fine work titled Explanation in History, in which he draws attention to the limitations of Hempelian explanation, at least when it comes to history. First, historical events are non-recurring. They aren't like balls that roll down inclined planes or objects dropped from a height. Accordingly, it isn't even clear as to what a general law would cover in the realm of history. Second, what gives an historical event its character, its intelligibility, are the specific persons, their motives, the contexts, etc. There really is no Battle of Waterloo without Napoleon actually, without events in Europe at that time, without the aims and strategies adopted by particular nameable persons. The Battle of Waterloo cannot be explained except in such terms, and surely not by involving some sort of impersonal law. And what is true in history would be the same where actual persons with actual highly individuated needs, judgments, aspirations constitute the events to be explained, and indeed bring about the events to be explained. So what is missing in the Hempelian account of physical events is a place for actual causal powers as being responsible for those events. It's not the meter reading empty that stops the car. We need real causal powers in any defensible explanatory scheme. And what is missing in the Hempelian account of social or psychological events is a place for reasons and motives and desires as being responsible for what's taking place. Now, it was one of the objectives of the logical positivists to rid science of metaphysics. And for some, this meant doing away with all occult forces, hidden powers, and the like. Nonetheless, it would strain credulity to believe that the lawful, time-ordered sequences in the natural world come about without the participation of just such forces. Gravitation finally refers to some feature of physical reality, as a result of which objects behave in predictable ways toward each other. The behavior is not simply reliable, but seemingly necessitated. What is more obvious than the reality of such necessitating powers when we consider space travel, high-speed computers, even the kitchen dishwasher? Such achievements and inventions are based on laws of science, and it's owing to these very laws that these achievements become possible. So we're very strongly inclined to accept as valid expressions of what really is the case just those laws that produce such success. We find in the laws of science the real structure of reality, the truth behind the merely cluttered pictures of everyday life. So there's a position we can take in philosophy of science. Now, against this very reassuring view, however, several powerful arguments have been directed. The struggle is between groups somewhat ambiguously or misleadingly designated as realists and anti-realists. The former, the realists, are those who regard the laws of science as reflecting reality as in itself it really is. Now, on this understanding, scientific laws work because they are expressions of how things actually, really are. The laws being the very mirror of nature. Now, the anti-realist perspective takes such laws to be very useful generalizations, valid within the contexts in which they were developed, but scarcely sufficient as accounts of all that really is the case. One of the leading defenders of the anti-realist school is Princeton's Bastian von Frassen, who made the case for his position most cogently in a 1980 book titled The Scientific Image. Now, he too focuses on the nature of explanation, but treats it as a highly contextual matter. What counts as a good explanation for von Frassen is not the logical structure of the argument, but the extent to which it answers a why question that arises within a given context. The quality of the explanation, then, is inextricably bound up with the interests and aims of those who have raised the question. So whether or not the best answer to why is this car stalled is rendered in terms of the principles of internal combustion engines, or a misunderstanding as to who was supposed to fill the tank, is not going to be settled simply by declaring the scientific explanation as correct. The car is stalled because Jack was supposed to fill the tank and he didn't. That's a good explanation. And in the circumstance, it might be far superior to all sorts of statements about internal combustion engines. In both cases, the usefulness of the concept of cause is finally what preserves our commitment to causal explanations. It's a pragmatic criterion that finally will vindicate causal concepts, surely not something seen to be at work in the world. Science does not discover real causes on von Frassen's account, but provides accounts in which causal concepts simply make the cognitive part of explaining more useful. There's another criticism of scientific realism, well exemplified in a 1983 book by Nancy Cartwright with the wonderfully controversial title, How the Laws of Physics Lie. Her thesis, developed with cogent arguments and highly technical examples and findings, is that the laws of science are really highly idealized accounts of reality. The idealized world in which the laws are unfailing is a world occupied by no one in the real world, physicists included. She puts it this way, quote, "Fundamental laws do not govern objects in reality. They govern only objects in models," close quote. Now, as she notes in her more recent book, a 1999 book called The Dappled World, reality in fact is disorderly. It's contextually fluctuating. It's resistant to any set of simple and simplifying laws. Ruled out as not merely impractical and impracticable, but contrary to fact, is the proposal to reduce mental, social, and economic realities to some more basic science. As she says in The Dappled World, by way of rejecting such reductive strategies, quote, "Laws hold as a consequence of the repeated successful operation or what I shall argue is reasonably thought of as a nomological machine, close quote. The solar system is such a machine. But in this, it is an uncommon feature of what is generally a highly dappled world. Cartwright rejects all realist conceptions of laws, but she is herself a realist about what she calls capacities. Now, given something like a nomological machine with such stable capacities as are immanent in matter, we are often enough able to make and able to record regularities. In her words, the nomological machine contains, quote, a fixed enough arrangement of components or factors with stable enough capacities that the right sort of stable enough environment will, with repeated operation, give rise to the kind of regular behavior that we represent in our scientific laws, close quote. Cartwright's position is not radically anti-realist. Rather, she identifies her target as a scientific fundamentalism that simply leaves insufficient room for reality itself to gain entry. Now, I would take her opposition to fundamentalism as drawn from the same considerations that led William James to reject what he called the block universe. The great obstacle to the progress of our understanding is always complacency. A fundamentalist scientism risks developing a hostility, at least an indifference, toward criticism, and thus it risks depriving itself of its own traditional sources of inspiration. Now, the realist reply to this line of criticism takes several forms. To begin, few scientists engaged in serious and fundamental work regard their activity as driven by considerations of what might be called cognitive security. The undertaking is predicated on the assumption that there really is a reality out there and that scientific laws can be derived with which to understand it, predict it, yes, control it. On yet another plane, the realist presents to the anti-realist not only such achievements as space travel and quantum electrodynamics, but a challenge. What inferences about these achievements lead to the best explanation of them? Now, let me pause for a second and rehearse that. Suppose you wanted to account for the success itself. That is, you have a problem of explanation here. What's the best explanation for success in attempts to get to the moon and back? Thus does the realist invoke the concept, an important one, of, quote, inference to the best explanation as a defense of realism itself. It goes something like this, an all too brief summary. First, NASA's space program was based on the assumption that the laws of classical physics and the accuracy of available instruments would provide an account of reality. Second, based on this assumption, rockets were built, astronomical calculations were performed, a date was chosen, and a launching took place. 3, astronauts reached the moon and then returned safely to Earth. Now, what's the best explanation of 3? The best explanation of 3 is that the laws that were accepted in 1 and 2, the laws accepted in 1 and implemented in 2, capture the very fabric of reality as such. So we see in these debates a far less tidy world of science than one that's depicted in schoolroom textbooks. Now, for all its achievements at the technical level, and indeed the theoretical level, science is nonetheless a human product. It will always bear the mark of the maker on the works. Judgments will vary as to the nature of this mark, whether it's indelible, whether it obscures the very reality to be understood and explained. It is to the credit of Thomas Kuhn that these very questions took on something of an urgency after the appearance in 1962 of his book, The Structure of Scientific Revolutions. In that work, Kuhn drew attention to the guild-like nature of the scientific community, where membership requires a set of shared beliefs, confidence that one's community has privileged access to the truth. Retaining membership in that community, on Kuhn's understanding, calls for the regular rehearsal of what the community has achieved, this in the form of repeated studies of the same sort, often with monotonous repetition. Thomas Kuhn referred to this as, quote, normal science, close quote, to distinguish it from those really radical departures that constitute the truly revolutionary changes within science. Now, as with Nancy Cartwright, Thomas Kuhn expressed concern over the very strong impulse to compress and distort reality in such a way as to make it fit in to what prevailing modes of scientific inquiry required. He also drew attention to the corporate aversion to novel findings, that square peg that will refuse to be compressed into an ideological round hole. Kuhn put it this way, quote, men whose research is based on shared paradigms are committed to the same rules and standards for scientific practice, close quote, this guild-like matter. Now, commitments of this sort will lead most to engage in nothing more elevating than a kind of mop-up activity in which one shows the community that one has mastered the tricks of the trade and can use them to produce conventional copies of the standard fare. The remarkably overlooked feature of the enterprise is that the research guided by such considerations unearths what was really very well known in advance. It's the same set of commitments, the same etiquette, we might say, that will dictate that which problems are to be chosen in the first place, the extent to which they promise fairly ready solutions. You don't take on things likely not to succeed. Now, many have rejected one or another part of Kuhn's critique of science, his attempt to understand science. Karl Popper, the eminent philosopher of science and logician, referred to Thomas Kuhn's reliance on the concept of ruling paradigms as what Popper called the myth of framework. Popper drew attention to the intuitive, passionate voyages toward discovery characteristic of all worthy science, and he rejected the sociological account of what makes problems significant. Of course, Popper himself had made an important contribution to philosophy of science in his critique of verificationism and his alternative methodological standard of falsification. It was something of a maxim in the scientific positivism of the 1930s and 40s that the meaning of statements was nothing more than the method by which they could be verified. And the further proviso was that those statements that did not lend themselves to empirical modes of verification were quite literally nonsensical in that no supporting sense-based evidence was available. Now, on this understanding, statements immune to empirical modes of verification were declared to be meaningless, merely argumentative. But it was Popper who was quick to observe that such a standard would render the very laws of science nonsensical. After all, a scientific law is universal in its reach, meaning that a candidate law would require an infinite number of verifying attempts. Now, as that's impossible, scientific laws would fail the verificationist stricture, and so he replaced this with falsificationism, making clear that though a law can't be verified an infinite number of times, it need only be falsified once or twice, etc., to lose its credibility. Now, falsificationism itself, a fixture in science, tells against Thomas Kuhn's notion of science as hostile to criticism. What is more challenging than a strategy that commits one to find fault at every level, to falsify wherever possible? So at the end of the day, a journey to the moon and back looks like something calling for a firmer grasp of reality than can be gained by obedient, normal science, or a science so idealized as to make little contact with what is really there. Getting to the moon and back is largely the work of rockets, once the basic laws and the necessary engineering have been worked out. And so the question that survives, even in the wake of so momentous an achievement, is whether those laws and that engineering are drawn from a culture, so to speak, that is to have pride of place in the matter of assessing all of reality. The word itself, reality, presupposes a precipient. It's not a sophist's trick to ask whose reality, or reality in relation to what. The aim throughout is to understand the setting of our own lives, at once physical, social, political, and moral. And it remains to be debated whether ultimate authority in these respects is held by science.